In this poster, I would like to talk about the integrated analysis of single-cell multi-omics datasets using Tensor Deformation method based upon feature extraction. My name is Y. Taguchi. I came from Department of Physics, Chuo University, Tokyo, Japan. The content of this poster has already been published in this paper. So if you are interested in the details of this poster, you can check this paper later. Introduction. So purpose of this talk, poster is integrated analysis of single-cell multi-omics data set, but it is usually difficult. The primary reason why it is difficult because the number of features in individual omics very differ from each other. For example, number of genes at most 10 to 4, but the number of methylation site or accessibility is up to 100 million numbers. Then secondly, usually these values are full of missing values. Even if for gene expression profiles in single-cell based measurement, more than half of genes are missing. And in the case of DNA methylation, the DNA accessibility, almost all of them are missing values. So in order to integrate these very sparse data set, usually we have to take care of the preprocessing so much. But in this poster, I propose usage of tensor decomposition, which enables us to integrate sparse multi-omics massive data set in very easily without careful preprocessing. So first, I would like to explain single value decomposition in order to explain tensor decomposition. Single value decomposition is a decomposition of matrix of the size of n times m into a product of n times L. L is a smaller number than m or n, and multiplied by diagonal matrix L times L. It is the weight of individual sum, and it is multiplied with L times m matrix. L is also small. Then mathematically, this expansion can be written like this. So this is a number of products with these terms, and this is the vector attribute to the I, and this is the vector attribute j, and this represents weight. Then tensor decomposition is extension to tensor. So tensor has more than 2 suffixes like x, I, j, k, and usually I is represent the genes, and j and k are represent of different experiments. For example, this is samples, this is tissues. It also can be decomposed into this form. This is vector and matrix attribute to fixed suffix j, and this is attribute to vector I suffix I. Usually this is genes, and this is attribute vector k, which is usually attribute to another kind of sample. So this is tissue and human beings and genes, and this is the weight of product of these 3 vectors. This expansion can be mathematically written like this. This is the weight term. This is the ice component L1 vector, and this GS component L2 vector, and the KS component L3 vector. This product summing up to reproduce original tensor. Then if we would like to apply this tensor decomposition to integrate analysis multi-omics dataset, we have to modify the original tensor like this. As I have told you, the individual omics data, for example, this is omics data for case omics data, and I is genes or methylation site or accessibility, and J is the cells. Then the number of features attributed to the case omics data set is different. For genes, it could be 10 to false. And if we consider the DNA methylation, DNA accessibility, this should be 10 to 8. And M is the number of single cells, the K is the number of omics data. So in this analysis, we employ K equals 3 because we will integrate the G expression and DNA methylation and DNA accessibility. And since the NK differs from between gene expression and DNA methylation, the DNA accessibility, we can apply the tensor decomposition as it. In order that, first we apply the singular value decomposition with individual omics datasets like this. This regarded via N, yes, so NK times M matrix, and apply the singular value decomposition. We have this expansion, this attribute I, this is the genes or methylation site or accessibility, and J attribute to the cells. Then original matrix Xijk projected onto go to this vector attribute to I represent a gene or methylation site or DNA accessibility, and original tensor converted to the LJK. The J is JS single cell, the K is K merging theta, L is the L vector generated from this expansion. Now, if we consider first large L vectors for all of 3 omics dataset, we have same number of features for all omics dataset. Because of that, we can apply the tensor decomposition to XLJK in contrast to the XIJK, which has different number of feature NK. Now XLJK has same number of feature L independent of K. Then singular value decomposition can be applied, and we have get this expansion. The difference from previous one is this part. This part is a vector attributed I, but now this is attributed L. And this is attributed to cells, and this is attributed to the omics dataset. Then we can have some representation for just single cell, and we employ the first 3 L's. Here we employ LK10, so first 30 vector attributed single cell. This means the single cell is represented as a 30-dimensional vectors, and we apply UMAP to this dataset. And the dataset Y is taken from this GeoID, and this represents the single cell human OCY maturation process, and the number of cells, single cells measures this number, and it is measured for G expression, the DNA methylation, the DNA accessibility. For dataset 2, it's very similar. It is also obtained from the Geo using this GeoID, and the number of cells, single cell measures is this. But for G expression, only this number of single cells are measured. And it is also measured the DNA methylation, the DNA accessibility, and the G expression. And this represents the 4-time point of the mouse embryo. Now we applied UMAP to the this vector attributed to the single cell L, J, using this formula. As you can see, cells, single cells, each point represents one single cell, and it is obvious they are well separated according to the classification. This is a 4-time point. This is a type of cells generated by differentiation. So this means our method can have some 30-dimensional representation by which you can map the individual cells with in the waves consistent with the classification. Next, we'd like to see if this representation is biologically reliable or not. In order that we would like to select genes whose expression coincident with this kind of placement. In order that, first we would try to which vector attribute cell line cells coincident with classification. In order that we apply category regression like this, so this is a JS cell. If JS cell belong to S classification, this is 1, otherwise 0. Then the BL2S and the BL2 is some regression coefficient, and we apply the categorical regression formula representing this to UL2J. We can get which L2J is coincident with the classification. Then we have found for data set 1 to 2, 18 L2s are coincident with classification, and they are associated with a correlated p-value less than 0.05. Then you want to see which vector attribute genes are associated with this vector attribute to the cell line, single cells, and coincident with classification seen here. We try to find to get which EG L1, L2, L3 has largest absolute values if we summing up L2 and L3. And summation L2 are taken only over 18 L2s selected in the previous slide. Then we have found L1, which has largest this summation, which is supposed to be most coincident with the classification of a single cell seen in this figure. Then we UL1I derived who selected L1L with this formula, and we get p-values using this formula. This formula means obtained derived UL1I obeys Gaussian distribution, and this L1I is very large absolute values. Even if we consider that it obeys Gaussian, it is regarded to be outstanding genes whose expression are most coincident with these classifications. And we have selected 45 genes and 179 genes are selected for both data set 1 and data set 2 respectively, because they are associated with adjusted p-values less than 0.05. If we assume this value obey with Gaussian distribution. Then enrichment analysis was performed towards these genes in order to validate selected gene biologically. So this is a data set 1, and as you can see, several enrichment analysis is coincident with process where the data set 1 is measured. So these numbers are referenced in the original paper. So if you are interested in the details of these references, you can check my original paper. And the data set 2, we also have many enrichment result. And so it is again our gene selected by our method is coincident with the result. And this suggests the TD-based answer if we collected selected biologically reasonable genes. Not only it can produce the representation, 30-dimensional representation of single cells, which is coincident with classification. So our result is not only useful to generate embedding, but also biologically reliable. And in addition to this, the one point I would like to emphasize here. as I have already emphasized, so gene expression data and DNA message data and DNA accessibility data is full of missing values. For gene expression profiles, non-zero components less than 30%, and for these two non-zero percent less than 10%. So these data sets are full of missing values. And usually we need careful treatment to integrate these three data sets, but we can generate 30-dimensional representation of individual single cell without doing anything special treatment. Just we have applied the single value decomposition to individual mixed data and projects on individual tensor onto this obtain the single value vectors, and then we apply higher order single value decompositions, and we get vectors attributed to genes, attributed to the cells. This is the conclusion. The tensor decomposition is an effective method that can integrate single-cell omics dataset as it is without processing individual omics dataset specifically. So I'm very glad if you can read my paper and understand what I have done in detail. Thank you very much for your interest.